Now that we've learned a little bit more about how hydrocarbons and organic molecules are represented with their skeletal structure, we can begin to investigate molecules and how they interact with the body a bit more, which is really what's more interesting as far as chemistry for healthcare needs. So, hydrocarbons are molecules that only contain carbon and hydrogen, and these are nonpolar or hydrophobic. They repel water. They're unlike water, right? I think when we look at these, we want to think carbon is very different from water, and when we add oxygen and nitrogen, we become more like water. Because how much carbon does water have? Well, it's got no carbon. Water is only one oxygen and two hydrogens. And so it's kind of like a big exception because it's really a very, very important part of biology. It's a very, very important biological molecule, but it's the one that doesn't have any carbon. And this non-carbon thing is facilitating so much of what goes on. And so when we look at molecules, how attracted are they to water? That determines a great deal of things. And the more oxygen we add to a molecule, oxygen or nitrogen, the more it's going to tend to want to like water. And these are broad distinctions. You know, what determines nonpolar versus polar? There is a bit more to it, but we really can get to an answer with this general guide to begin with. And so polarity is really, really important because the polarity of a molecule, the way it wants to interact with water, is going to determine whether that molecule is soluble in either blood or in fat, blood being mostly water. Nonpolar drugs are going to be fat soluble, and polar drugs are going to be water soluble, dissolving in the blood much more easily. And so the principle here is a big chemical principle, like dissolves like. Polar substances are more like water, they will dissolve in water. And more specifically, because they're like water, they form chemical interactions with water. Nonpolar or lipophilic, fat-loving substances will dissolve in fats or lipids. These will be attracted to fats and lipids, and the cell wall is a lipid bilayer, and so that's a really important part of what these lipophilic substances will interact with. Blood and urine, mostly water. Cell membranes are lipid. So looking at a substance will tell us which of these parts of biology they'll be more attracted to. And so let's kind of step back and let's remind ourselves of polarity. And let's look at the following molecules. Are they polar, meaning hydrophilic, or nonpolar, meaning hydrophobic? Take a look at these and see if you can come up with a conclusion. And I'll pause the video here. Okay, so for this first one, this would be hydrophilic. It's got an OH on it, and that's a big sign that it wants to be a bit like water. It's kind of like half of water, just with an extra carbon attached to it. OH is present, this is a polar molecule, and this one is going to interact with water, hydrophilic. And what about this second one? Well, this one is hydrophobic, and I wouldn't really call this lipophilic because this isn't really a molecule that we're going to see in biology, but hydrophobic in biology would lead to being fat-loving, lipophilic. It's all hydrocarbon, it's a nonpolar molecule, and therefore this one is going to be, attracted to fats rather than attracted to water. And I think that as you're just getting started, look at the relative amount of oxygen and nitrogen that are in a molecule. Many molecules will be so complicated that they're just going to have at least some polarity, but noting the relative density of oxygen and hydrogen, or of oxygen and nitrogen, that will be a great guide towards determining this. And again, this is a huge distinction because when we look at polarity, fat-soluble drugs nonpolar, water-soluble drugs polar. And this determines whether the solubility will be in lipids and membranes or in blood and urine. And because of this, the storage system is going to be very, very different. Fat-soluble drugs will be stored in the fat, and therefore it's going to be kind of slow to get those out of our system. We need to metabolize the fat and unlock those drugs stored in the fat in order for them to be metabolized and move through our biological system. Water-soluble drugs, on the other hand, are already part of the blood and the urine, and this is just kind of on the highways of our biology already, not stuck in the warehouses. And because of this, the clearance of these drugs is pretty quick. For barriers, this is another really important thing, because for fat-soluble drugs, these could clear barriers pretty easily. And the ability to clear barriers is going to be pretty dependent on the size of the molecule, but the fact that it's not inherently water soluble, preventing interaction with the lipid bilayers, is going to make it have potential to cross barriers like the BBB, the blood-brain barrier, or cell membranes. So being nonpolar means that we should consider whether this can enter cells compared to water-soluble drugs, which are going to have a difficult time entering cells on their own, but could be able to be facilitated based on if the cell has transporters. This is kind of to say, if the cell wants to take in that molecule or not, it may have the means to do that, and if the water-soluble drug is not able to be transported into the cell via its channels, then it's just not going to be able to squeeze through the wall of the cell. The fat-soluble drug, that may be a much more of a possibility. Okay, let's take a look at two really well-known drugs, and maybe you can identify these drugs here as well, but what do we think about these? Are they soluble in water? And if we say solubility, I think that generally would mean water solubility, but let's identify these as lipophilic or hydrophilic and try to think of why. I'm going to go ahead and pause the video here and see if you can come up with these answers. Okay, so for the one on the left, this is fentanyl, and this is highly lipophilic. It's almost all carbon. Yes, there's a little bit of nitrogen and oxygen, but the fact that these aren't connected to hydrogens by being at the end of the molecule means that they're kind of like substituting for carbon, and they're more like carbon than an oxygen or a nitrogen that's at the end and would contain, hydrogens attached to it. Fentanyl is obviously a very, common and important drug to know about these days, and part of the reason why it's so potent is because it's highly lipophilic, which is not only based on the fact that it's almost, it's mostly carbon, but also that it's relatively small. This may not look like something we should consider a small molecule, but it is. It really isn't like big, very large. Some larger molecules could be up to, 1,000 grams per mole. It could be, really like 100 carbons isn't out of the realm of possibility. This is still considered a pretty small molecule, and because it's small and because it's lipophilic, fentanyl is very easy to transport around the body. That's a big part of its potency. What about this second structure? What do we have here? Well, this is metformin, and this is a highly hydrophilic molecule, and I hope you were able to get to that. It's got many nitrogens. Again, nitrogen and oxygen, they kind of function rather similarly, and a lot of these have hydrogens attached to them. This makes this mostly nitrogen, not mostly carbon, and therefore very much wants to interact with water. This is a drug used to manage blood sugar and used to treat type 2 diabetes, and is also another very popular drug. This one water soluble, and that's how it's able to transport around and facilitate that interaction in a way that's been found to be highly effective.